All right. Hey, everybody. Welcome back. So this is video for activity sheet 2, integration by parts. Here we will introduce another integration technique. And just like how U substitution was based on the chain rule, this new technique, integration by parts, will be based on the product rule. So as a reminder, the product rule said that if you had two functions and you wanted to take their derivative, so here we have we have u and v. They're being multiplied together. That's what the product in product rule comes from. And we're taking the derivative. Then the derivative of u times v, well, that was u prime times v plus v prime times u. Right? And so the method of integration by parts will recognize that associated with this derivative rule is an integration rule, specifically that if you are trying to integrate the expression on the right, so that's u prime times v plus v prime times u. So if you were ever trying to integrate something like this, then the end result would just be u times v plus your additional constant there, right? And we're going to see how we can use this to integrate some more challenging expressions. Let's scroll below. So let's try to calculate first the derivative of x times sine of x. Well, this is, of course, a product. And so its derivative, we get f prime, that is equal to, so it's just the derivative of x, so we just get 1 times sine of x plus x times the derivative of sine, so x times cosine. All right, and then we see how we can use this to calculate the integral below. So without thinking too hard, we can calculate integral a, right? Integral a is just what we have here, is exactly the same expression that we had up here. So according to our integration rule, this should just immediately become, what was it? It should immediately become x times sine of x plus a constant, right? This is, again, sort of using this rule up here to calculate this and using the fact that we've calculated the derivative of x sine of x. So that we get immediately just by virtue of recognizing that it is the end result of a product rule. Slightly more interestingly, we can try to calculate problem B, right? And problem B is kind of challenging. Problem B is not the end result of a product rule, but instead it is one part of the previous product rule, right? So it is this piece right here. And here is where we can start to get a little tricky or start to get, a little clever. We might recognize that this is part of the previous product rule result, and we can try to take advantage of that in order to solve this integral. So let's see what we can do here. Let me clear some of this. Okay, so jumping up to problem A for just a moment, I'll keep writing up there. Notice that this integral expression is also equal to just the integral of sine of x plus the integral of x times cosine of x, right? We can split the integral across the addition sign like that. Right? So in fact, when it comes time to calculate x times cosine of x, I can calculate this and isolate it simply by subtracting the integral of sine on both sides. And so when it comes time, again, I'll skip down below now. When it comes time to calculate the integral of x cosine of x dx, I can simply recognize that this will equal x times sine of x. I'll hold off on the plus c for a moment, minus the integral of sine. And of course, we can calculate the integral of sine, right? The integral of sine is negative cosine. And so this becomes x times sine of x minus negative cosine. So that's plus cosine, and then plus our additional constant over here. So first of all, if we weren't completely confident in our answer, right? And sometimes we want to, just double check, make sure that we're happy with us. One thing that we could do is that we could simply take the derivative of our answer and see that we got x cosine of x back as a result. So let's really quickly, if we take the derivative of x sine x plus cosine x, right? We do the product rule at first, so we get sine x plus x cos x. Okay, and then plus the derivative of cosine. The derivative of cosine is minus sine. And in fact, we see that that positive sign, that negative sign cancel, and the answer we get is just x cosine of x. So this is just some confirmation that yes, in fact, the answer we get down here by taking the derivative of that is equal to the thing we were originally trying to find the antiderivative of. So just more confirmation that this answer is in fact completely correct. Check. All right, so this next question asked, what's different about the two integrals up above, and how did we solve part B? Well, as we saw in part A, we were asked to recognize that sine x plus x cos x was the end result of a product rule. And then we just integrated directly once we realized that. For part B, right, slightly more challenging, we had to recognize that x cos x was a part of the end result of a product rule, but not the whole thing, right? And it involves some clever use of this, this first piece, the sine piece here, moving it over to the other side of the equation in order to really solve part B. So with that in mind, let me scroll back up and look at this equation, this equation over here. I want to write that in a more usable form and sort of following in the same footsteps as what we did below. Notice that the left-hand side can be broken up into two pieces. So we get the integral of u prime times v dx plus the integral of v prime times u dx. That's equal to u times v plus a constant. And then I'm going to go ahead and subtract one of these two pieces to the other side. And to get the formula looking like it classically is, I'm going to subtract this first piece to the other side. So we end up with the equation. I'll write it as is for a moment, and then I'll tweak it to make it look a little fancier. But we get v prime times u equals uv, and then minus, because we've subtracted this over, the integral of u prime v. More classically, we tend to write this in the following two ways. So we either write, right, I'm just going to flip the position of u, and then we get v prime dx equals uv minus the integral. Here we get v, and then there's our u prime. Another way that we classically write this is we sort of condense the v prime and dx. So we simply write that as dv. And then here we condense, oh, I've forgotten my dx's over here. Let me throw those in quickly. Dx, dx. All right, and then over there we can write the u prime dx, write that as du. So the classic way, or another classic way to write this equation would be to write u dv, the integral of u times dv equals uv minus the integral of v times du. And this is just sort of a stylized way of writing this equation, which I would call sort of the most important equation. That got away from me a little bit there. But that middle equation there is what I call the most important equation, and that's going to be the one that's on the slide below. So this is our integration by parts formula that we see right here. Okay, so when we get in a problem that looks similar to the problem we saw above, the x times cosine of x, what we will often do is we will try to recognize that the x times cosine of x fills this sort of form, right? Where one of the pieces can represent or be represented by the function u, and one of these expressions can be represented by the function v prime. When we choose u and v prime, we calculate u prime and v, and we plug it into this formula here. What that means is that we end up solving one integral equation, sort of this first integral equation, and we end up getting an answer that has in its form a second integral equation. But the hope is, if we've been clever in our choices of u and v, that second equation will be a little bit easier to compute than the first equation. So we're going to leave it there for this video. There's lots of practice problems here that we can enjoy. So I'll see you next time.